Hello all, welcome to Monologues. Today's lecture will be on a particular communication bus known as CAN bus. So the full form of CAN bus is a controller area network. It is majorly used in automobile industry for the control of the various parts in a normal car or normal vehicle. So there are many communication buses, the communication methods in embedded system, like the SPI bus, the I2C bus, and so on. So why did we require a new method, a new communication method? The number one reason is the distance between individual parts in the car. Or imagine the size of a car, and we need different sensors and different controllers in different areas of the car, and each of these units needs to be in sync with each other and needs to communicate with each other. So a normal control bus or a normal communication bus like the SPI or the I2C will not work in those situations because they are small. That is the primary reason why we need a new method of communication, which is a CAN bus that we are going to be discussing right now. So by definition, what is a CAN bus? It is a multi-master serial communication bus whose basic design specification call for high speed, high noise immunity, and error detection features. Because these are the features we need in a communication protocol, and we are developing a new method and we need these features. So just remember these points: the multi-master serial communication, and we need features like high speed, high noise immunity, and error detection. So we'll go in detail. What is a multi-master and how it is deployed in this communication protocol? So it is basically through a method known as functional addressing. So what is functional addressing? As you can see on the screen, data messages do not contain source or destination addresses, only identifiers relating to their function and or priority. This means, like in most of the other communication protocol, there is one master and there are many slaves, and the master determines which message should go to which part. But here, every single node itself is a master. There is no slaves here. Everyone is a master. Everyone can transmit data and everyone can receive data. And this is made into a practical situation through this method known as functional addressing, which uses an identifier. An identifier is a 11-bit code, a pre-programmed code that helps you to prioritize which message is it has a higher priority than the other. So we'll go in detail about that in the later slides. So the next criteria or next feature is high speed. It offers data communication up to 1 megabit per second. Noise immunity, it is made possible by a method called differential signaling. Then error detection, it automatically retransmission of faulty messages and bus disconnection of nodes that are suspected to be physically faulty. So through these two methods we attain error detection. And there is one more one very important and very cool feature, is this hot plugging. That is, even when the communication bus is in active mode, like it is operating right now, even then also we can remove one node, also add a new node. It doesn't actually matter to the bus or the communication methods, because everyone is a master, everyone can send, everyone can receive. There will be no difference. So hot plugging is a very cool feature, and it's a very important feature also, because it makes us very able to add new elements or remove faulty elements. Makes engineering much more easier. So this is what a typical CAN bus node looks like. And this is our typical CAN. The entire diagram shows a typical CAN bus. We have 3 nodes: node 1, node 2, node 3. And let's look in detail about the inside of a node. The node contains an MCU, a microcontroller unit, which itself is a CAN controller. We are using one small MCU in a node because we want to control that node. So that CAN controller is being done by the MCU. And from that MCU, from that CAN controller, we have one TX and RX. That is one transmitting signal and one receiver signal. And this TX and RX is given to another module known as CAN transceiver. Now, why do we have a CAN transceiver? Is because we need differential signaling for error removal. So we have two lines known as CAN low and CAN high. So to give a differential signaling, we need to provide TX and RX to CAN transceiver, which in turn converts the signals to the required format and gives it to the CAN low and CAN high lines, which will in fact create a differential signaling. And we have a terminating resistance at the each end of the R due to double wave and other problems that we know in electrical engineering. And as you see, there are two more nodes connected in the same way. So this is how a typical node looks like. Moving forward, differential signaling. Now we look into what differential signaling is. So single-ended signals, that is the normal signals that we know. There are two levels to it, like one high and one low. We only know the logic 1 represents the high and the logic 0 represents the low level. So the problem with this is we have a lot of error signals around our environment. So in whichever signal that we give or we input, the error signals will add on to it, and there will be no method to, there are methods like to filter out, but still we won't get a pure signal, pure input, because of the error signals that are getting added onto it. So how does differential signaling solve this? This is how we provide two signals which are complement of each other and 180-degree out of phase. So as you can see in the figure, we have one +5 volt, that is the blue wave, and -5 volt line, which is the yellow wave. So we have two signals which are complement of each other in value. That one is +5 and one is -5, and they are 180-degree out of phase, as you can see in the figure. So the logic 1 over here is basically the difference between the two signals, and logic 1 and logic 0 are the difference between the two signals. So in logic 1 state, it will be +5 minus -5, which will give you 10 volts, and the logic 0 will be -5 minus +5, which will give you -10 volt. So we have two levels. We have achieved two levels, 10 volt and -10 volt for logic 1 and logic 0. So our needs, the binary needs, won't have any problem. We get the same input itself. But with this, we are eliminating or removing the error signals that were individually added to each of these signals. By subtracting these two signals, we thereby subtract the error signals also. So we get to remove all the errors. So that is solved, that is sorted out. Now moving forward. Now, dominant and recessive states in a CAN bus. This is the most important part, and this is how we'll see about how the CAN bus actually works. So what is a dominant and recessive state? We'll look into it. So as you can see in the picture, and we have two letters defining the recessive state and dominant state. So there is an R section and there is a D section in the figure A. So beneath that, I have written something like the logic 1 is represented by a CAN high of value 2.5 volt and CAN low value of 2.5 volt, whose difference will give 0 volt, and hence the recessive state, 0 volt recessive state. But the one thing that we have to remember is the recessive state, or the 0 volt state, basically represents the logic 1. It's contrary to what we do conventionally. So logic 1 is 0 volt recessive state. Logic 0, on the other hand, has a CAN high value of 3.5 volt and CAN low value of 1.5 volt, whose difference will give a 2 volt value, which is a dominant state, which is a higher state. So we have achieved two levels. the 2 volt dominant state level and the 0 volt recessive state level. But remember that logic 1 is recessive and logic 0 is dominant. We need to remember that. Okay, and this what I've written beneath this diagram is what's shown in the pictures also. I hope you will understand that. Now, moving forward. So obviously, dominant is greater than recessive, or that's why the name itself, dominant, recessive. Dominant is bigger than recessive. So if you have two signals, one dominant signal and one recessive signal, obviously the dominant signal will win. So that is how we determine everything in the CAN bus communication protocol. So as I have written over here, the bus is won by the node that sends the dominant bit, thereby making the bus in dominant state. Same as I said earlier, if you send two signals, dominant and recessive, the dominant wins. Whatever is sent by the TX is sensed by the RX of the same node also. Why is this written in bold and why is this important? Because whenever a node, because we, as I mentioned earlier, this CAN bus system is a multi-master system that enables every node to send data and every node to receive data. So what will happen if two nodes simultaneously sends data? Which one will be received and which one will be processed? As we know, dominant wins, but there should be only one dominant. Hence, this bolded sentence, whichever value that I am sending, I will sense the same value from the bus, or I will sense the value of the bus immediately and compare it with what I have sent. So the explanation is also written over here. This means that the RX always senses the bus state and compares it with what it had sent to determine whether it has won the bus or not. So what will happen if it hasn't won the bus? It will go into a listen only mode or on the recessive state, and it will wait. It will wait for the bus to become idle so that it will try to send the data again. So we I've given a table over here which shows the green color headings are the signals sent by nodes A and node B, and the bus states are the gray colored rest of the cells. So when node B and node A sends in dominant signals, the bus state is dominant, which is won by A and B. It is not determined. So that is why we need priority identifier or 11 bit. We tried for 11 times in 11 bits. So one single thing cannot determine everything. So because of this, because two nodes can simultaneously send in the dominant, we don't know which has won the bus. Moving forward, dominant node B sends dominant, node B sends dominant, and node A sends a recessive. Dominant signal given by node B will win the bus. Going down, the recessive signal given by node B and dominant signal given by node A. The dominant signal given by node A will win the bus. When both are giving recessive signals, doesn't matter. Nobody is winning anything. Okay, so moving forward. Explaining what I've just explained also. Let's read through it one more time. Imagine at time 1, when both node A and node B transmit dominant bit, the bus is now in dominant state. At time T2, node A puts a recessive bit and node B puts dominant bit. As the nodes sends back immediately the bus state while transmitting, node A identifies that the bus is in a dominant state compared to its recessive state, and thus node A will wait for the bus to get idle. Wait for the bus to get idle. That is the procedure. If you are not winning the bus, you will wait for the bus to get idle so that you can try again. That is the basic concept. Now, a bus is recognized as idle when the bus state is recessive continuously for 6 to 7 clock pulses. So a bus, that is the standard. That is a standard set by all the international people. So For 6 to 7 clock pulses, for 6 to 7 times, we need to get continuously recessive state to determine that the bus is idle and no one is sending any new stuff. So that is a standard. We use such standards while programming. Okay, moving forward. Like what I have explained earlier, that in theoretical technical terms I have written over here. CAN communication protocol is a carrier sense multiple access CSMA protocol with collision detection CD and arbitration on message priority AMP. So basically what is CAN communication in a very technical theoretical way, or like this is how we should answer if you're being asked this question, like what is CAN for an interview. Just simply say that it's CSMA/CD+AMP, and that means you know what the definitions or theoretical words are. So CSMA, that is carrier sense multiple access, CD collision detection, AMP arbitrary on message priority. So CAN communication protocol is CSMA/CD plus AMP. Okay, what does CSMA mean? CSMA means that each node on a bus must wait for a prescribed period of inactivity before attempting to send a message. That is what we have explained in the prior slide, that it will wait until the bus gets idle, a prescribed period. That prescribed period is what we have mentioned as 6 to 7 clock pulses. So that is what CSMA is. It waits, or bus must wait for a prescribed period of inactivity before attempting to send a message. What does CD plus AMP mean? That is what we are trying to achieve using that 11-bit identifier or the priority codes. CD plus AMP means that collisions are resolved. That is what the situation we tried to explain earlier, like two nodes simultaneously sending in the data. Which one should we receive? Which one is considered to travel through the bus? That is collision detection. Two nodes are colliding right now. Now that collision is detected and it is sorted out using AMP. That is CD plus AMP means that collisions are resolved through a bitwise arbitration based on a pre-programmed priority of each message in the identifier field of the message. The identifier field is the priority code, and the higher priority identifier, which will always be the least number value, which means number 1 is higher priority than number 2. The least number value has the higher priority. The higher priority identifier always wins the bus. So simple. So the basic theory of all of the working of the CAN bus is that is that the bus is won by dominant state. Dominant recessive, dominant is stronger, that's why the name dominant. So the bus is won by dominant state. Always remember, dominant means logic 0. So the bus is won by the dominant state. Hence, if a node sends recessive bit but senses a dominant bus, then that node goes into listen only mode. That's what I've tried to explain throughout the entire lecture. So I hope you have understood the basics of basics of CAN and how it all works. So enough with the theory, right? We should wrap this theory up and try to look at a practical problem. So let's scrap this theory. So we'll try and look into how the CAN bus actually works. I mean, the priority identifier actually works. So let's have a situation. We have 3 nodes, node 1, node 2 and node 3, each of with 11-bit identifier. The 11 bits in binary is given. So in the hex format, we know the value. Node 1 has 0x65D, node 2 has 0x676, node 3 has 0x659. Each node has a 11-bit identifier. 11-bit, that binary identifier is the 11-bit identifier, which is used to determine the priority. From the hex value, we'll easily identify that the node 3 value, the 0x659, is the least value among the entire 3 nodes. So which one has the highest priority? Node 3 has the highest priority. So basically the node 3 has won the bus. So we'll look at now we'll see how the controller, the microcontroller controlling all these things, will identify each bit and determine whether whether this particular node has won it or not. So let's go. What we have is the typical format of a CAN bus message. So we have the start, SOF start, and then the first of all the 11-bit identifier 0 to 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The MSB is 10, the LSB is 0. Then we have we have a space, bit space called RTR. Then the control, like that control actually determines whether you are sending data or trying to receive some particular data from someone, stuff like that. Then the actual data that the message that you're sending to the control bus. So we'll see. Let's start. Okay, so initially we are remember that we are using the previous example, the example that we just mentioned, and know that the node 3 has 1. We are using that same example. Okay, so node 1, node 2, node 3 at the start, before we are entering into the 11-bit identifier, at the start, what we can see over here, everyone is in logic 0. In the start, everyone is in logic 0. Before SOF, everyone was in logic 1. That means the bus was in a recessive state. And what does a repeated continuous recessive state mean? The bus was idle. So before we are getting into this entire control part of the message of the CAN controlling message given by the node, before SOF, every node or every signal in the bus is at a logic level 1, which means it was in a recessive state, which means the bus was in idle state. So every node can now send in data. So the SOF bit is always logic 0, which marks the starting point of the message. Which is sent by every node. That is a standard. Okay, now we are getting into the identifier part. So if you check the previous slide and find out about the binary values of node 1, node 2 and node 3, you can relate to this picture. So 10th bit and 9th bit are high logic 1 level for all of the nodes, node 1, node 2 and node 3. It is at logic 1 level, and 8th and 7th bit are at logic 0 level. So what does that mean? That means at 10 and 9, 10th bit and 9th bit was same for every node. The bus was in recessive state, and 8th and 7th bit were same for every node, and the bus was in dominant state, neither of which determines which node has won the bus, because in the earlier section, like two signals sending recessive, bus is recessive. 2 signals sending dominant, bus is dominant. Nobody knows which node has won the bus. So as of right now, up to the 7th bit, nobody knows. Now moving forward, 6th bit of all the 3 nodes are at a logic 1, which means the bus is now in a recessive state. When it comes to the 5th bit, for node 1, it is logic 0. For node 3, it is logic 0. But for node 2, it is logic 1. What does a logic 0 mean? Logic 0 mean it is at dominant state. Logic 1 mean it is in recessive state. So right now, node 1 and node 3 are sending dominant bits, whereas node 2 is sending a recessive bit. So as of right now, we can eliminate node 2 from the race about who is going to win the bus. So node 2 is out of the race right now. Node 2 has entered listen only mode, and the bus is in dominant state, as you can see. Now moving forward, the fourth bit. Okay, the fourth and the third bit are logic 1. So the bus is in recessive state. Nobody knows who has won the bus. Next part. At bit 2, node 1 went to logic 1 and node 3 went to logic 0. So node 3 is sending dominant bit and node 1 was sending a recessive bit at the second bit level. So node 3 is dominant versus node 1's recessive. Node 3's dominant wins. Node 1 went into listen only mode, and we can say that node 3 has won the race about the control of the bus. So node 3 right now controls the bus. So then later the second and the first bit, the 2th bit and the first bit are in logic 0 state, so they were in dominant states, and the 0th bit is a logic 1 recessive state, so it doesn't matter, and the RTR wasn't dominant. And then any data after that is any data the node 3. So the bus is right now receiving whichever data the node 3 is trying to send. So it's whichever data node 3 is sending. So I hope you have understood the process that we have just viewed over here, how it is progressing, and how each bit is being analyzed by the microcontroller, and each bit of every node is being compared to find who is ahead of everyone else in the race to have the control over the bus. So this is how the control of the microcontrollers in every node, because this is a multi-master and each node calculates this. This is how the controllers in every node determines whether they have a say in the bus or not. If they don't have a say, they go into listen only mode and wait till the bus becomes idle again. So I hope you have gained some information or some knowledge from this video, and please feel free to comment any doubts. Thank you for listening. Thank you for watching.